The borax they're selling you isn't for detox. It's being used to augment your very biology from the inside out. Borax acts as a cross-linking agent, combining with graphene and polymers to self-assemble into a network of microscopic biosensors. These create an internal network for electrical stimulation and controlled drug delivery. These hydrogels monitor your body's chemistry in real time, releasing medications or other compounds precisely when needed. These are not supplements or detox products. They are engineered, sophisticated medical devices.
Sensitive detection of borax in real food samples by red emissive carbon nanoparticle, displaying multi-format compatibility, including faraway smartphone-based sensing. Carbon nanoparticle was derived from alizarin red S and p-phenylenediamine. Carbon nanoparticle used for sensitive detection of borax through quote-unquote turn-on fluorescence response. Borax persuaded aggregation-induced intense red emission of carbon nanoparticle within 1 minute. Multi-format compatibility for versatile application with LOD, limit of detection, in micromolar range. Digital image enables remote sensing via color channel analysis through smartphone. Predictable chemical outcome is foremost important to obtain optical output and sensing mechanism that offer excellent leverage to the detection formats. This demonstrated herein the ultra-sensitive detection of borax in real food samples using carbon nanoparticle, an instrument-free, inexpensive, sensitive, on-site, and visual detection is achieved by engaging the surface functional groups of carbon nanoparticle to trap the boronate ion of borax as a cross-linker to enforce the optical outcome in the form of aggregation-induced emission. Drastic amplification of the red fluorescence of carbon nanoparticle after borax addition is achieved within 1 minute, with scope to extend the strategy to multiple formats, including 96 well and microfluidic device, irrespective of chemical interferences, with LOD and micromolar range. The digital images of red emissive aggregated carbon nanoparticle served as input for color recognition application of smartphones, whereby red, green, blue RGB channel values were extracted, making the detection possible from faraway location. And here we have a lovely image. Now let's go over here to ResearchGate, and we're going to read. Electrical stimulated polyvinyl alcohol borax graphene hydrogel for drug releasing and delivery. Polyvinyl alcohol hydrogel has promising applications in numerous biomedical, biomaterial, and tissue engineering. However, it has poor conductive properties, restraining its development with huge fields such as biosignals acquisition systems, thermal stability, and drug delivery. Adding graphene as a nanofiller will produce polyvinyl alcohol, borax, graphene, nanocomposite hydrogel, which is an excellent procedure to significantly improve the conductive properties of polyvinyl alcohol. The toxicity will not affect the nanocomposite, while very well dispersed graphene will significantly improve the thermal and conductivity stability of the nanocomposite. In this study, we investigated the performance of a newly prepared conductive hydrogel gel using the freezing/thawing method. Now let's go over here and read. Direct laser writing of chitosan, borax composites towards sustainable electrochemical sensors. In this study, the laser-induced graphitization process of sustainable chitosan-based formulations was investigated. In particular, optimal lasing conditions were investigated alongside the effect of borax concentration in the Chittisan matrix. In all cases, it was found that the obtained formulations were graphitizable with the CO2 laser. This process gave rise to the formation of high surface area, porous, and electrically conductive laser-induced graphene structures. It was found that borax, as a cross-linker of chitosan, enabled the graphenization process when its content was greater than 30 weight% in the chitosan matrix, allowing the formation of an LIG phase with a significant content of graphite-like structures. The graphitization process was investigated by TGA, X-ray, XPS, and FTIR spectroscopies. Now we're going to go over here. Two-dimensional self-assembly of boric acid functionalized graphene quantum dots. Tunable and superior optical properties for efficient, eco-friendly luminescent solar concentrators. Carbon-based nanomaterials hold promise for eco-friendly alternatives to heavy metal-containing quantum dots in optoelectronic applications. Here, boric acid functionalized graphene quantum dots were prepared using bottom-up molecular fusion based on nitrated pyrenes and boric acid. Such boric acid functionalized graphene quantum dots with crystalline graphitic structures and hydrogen bonding functionalities would be suitable model systems for unraveling the photoluminescent mechanism, while serving as versatile building blocks for supermolecular self-assembly. Unlike conventional graphene quantum dots with multiple emissive states, the boric acid functionalized graphene quantum dots exhibited excitation, wavelength, independent, vibronic coupled, excitonic emission. Interestingly, their PL spectra can be tuned without largely sacrificing the quantum yield due to two-dimensional self-assembly. In addition, such boric acid graphene quantum dots in a polystyrene matrix possess an ultra-high quantum yield and large exciton binding energy, benefiting from broadband absorption, ultra-high quantum yield, and long wavelength emission. Efficient laminated luminescent solar concentrators were fabricated, yielding a high power conversion efficiency. Now, let's go over here to Science Direct. One-step synthesis of boron-duped graphene quantum dots for fluorescent sensors and biosensors. Boron-duped graphene quantum dots are facile prepared using one-step hydrothermal process. Fluorescent sensor for sensitive detection of iron-3 is achieved with boron-duped quantum dots as probe. Fluorescent biosensor for detection of cytochrome C using boron-duped graphene quantum dots is demonstrated. Indirect detection of phosphate is achieved by recovery of iron-3 quenched fluorescence. Heteroatom duping can endow graphene quantum dots with various new or improved structural, optical, and physiochemical properties. In contrast to the widely reported oxygen, nitrogen, or sulfur duping in graphene quantum dots, simple and scalable synthesis of boron-duped graphene quantum dots with high yield and quantum yields remain challenge. In this work, boron-duped graphene quantum dots are one-step synthesized and serve as the fluorescence probes for the fabrication of sensors towards iron-3 ion or phosphate, as well as biosensor towards cytochrome C. The boron-duped graphene quantum dots are facile synthesized using one-step bottom-up molecular fusion between 1,3,6-trinitropyrene and borax in sodium hydroxide under hydrothermal process. The synthesis can be performed using large volume autoclave with high yield of 71%, indicating possibility for gram-scale production of boron-doped graphene quantum dots. The as-prepared boron-doped graphene quantum dots exhibit single or bilayer graphene structure, high crystallinity, uniform size, bright, absolute photoluminescence quantum yield of 16.8%, and excitation-independent green fluorescence. Successful duping of boron atoms in the lattice of graphene quantum dots enables high selectivity towards iron 3. Based on quenching of fluorescence, the boron graphene quantum dots by iron 3 turn-off model, detection of iron 3, and iron 3 rich cytochrome C are demonstrated. As phosphate can recover iron 3, quench fluorescence of boron graphene quantum dots. Indirect fluorescent detection of phosphate is also achieved with LOD of 340 nanometers. In addition, detection of iron 3, cytochrome C, and phosphate in real samples is achieved.
Borax can be used to create a variety of nanomaterials with diverse applications. These applications range from improving the properties of polymers and composites to enhancing the performance of sensors and catalysts. Borax serves as a cross-linking agent, a structure-directing agent, and a source of boron for doping nanomaterials. Applications of borax nanomaterials. Cross-linking agent. Borax can be used to cross-link polymers and create hydrogels with improved strength, thermal stability, and water absorption. For example, borax can be used to create cross-linked cellulose hydrogels, starch nanoparticles, and graphene hydroxyethyl cellulose aerogels. Structure-directing agent. Borax can promote the formation of hollow structures in metal oxides and metals. This method is scalable and can be used to prepare materials with high surface area and enhanced catalytic activity. Doping agent. Borax can be used to dope carbon-based nanoparticles with boron, improving their electronic and optical properties. Boron-doped carbon dots, for example, have been shown to have high photoluminescence and low toxicity, making them suitable for biomedical applications. Improved material properties. Borax can be added to nanocomposites to improve their conductivity, thermal stability, and flame retardancy. For example, borax cross-linked graphene hydroxyethyl cellulose aerogels exhibit excellent flame retardancy and compressive strength. Enhanced catalytic activity. Hollow Cu20 nanoparticles and Cu-Cu20 heterostructures, prepared using borax, have demonstrated enhanced electrocatalytic activity for glucose oxidation and hydrogen peroxide reduction. Sensor applications. Borax-based materials can be used to create non-enzymatic sensors for glucose and hydrogen peroxide detection. Strengthening concrete structures. Borax cannabinol nanorods can be used to strengthen concrete structures and prevent fractures in composite materials. Improved fuel properties. Borax decahydrate can be added to diesel fuel to reduce emissions and improve combustion characteristics. Bioimaging applications. Boronic acid-modified nanoparticles prepared using borax can be used for bioimaging applications.